Photoelectric effect.
Between 1888 and 1889, Heinrich Hertz, Wilhelm Hallwachs, and Philipp Lenard performed experiments that showed light of specific frequencies, that's over here, you can see the light right here and you're showing it as waves, that were incident upon certain polished metals. Here's the metal right here, and this represents the electron C, the electrons that are shared between all the different atoms in the metal. And at times, when specific frequency light hit this, electrons were emitted from the metal. The researchers found some pretty incredible effects. For example, below a certain frequency, a certain cutoff frequency, of the incident light over here, there were no electrons emitted. When you got a higher frequency of incident light, then electrons were emitted. Secondly, when they were emitted, the number of electrons were directly proportional to the intensity of the light, but the energy of these electrons was independent of the light intensity. So you could turn up the light and you would still not get any greater energy of these electrons. You'd get more of them, but they wouldn't have a greater energy. Also, the minute the light hit the metal here, you got electrons. They came out immediately. When you had the proper frequency of light, when you were above the cutoff frequency up here, the electrons would appear instantly. These properties could not be explained with the classical wave theory of light. Nobody could explain why this happened. If light were a wave, then these electrons should have been emitted no matter what the light's wavelength was. And if the light was more intense, then more electrons should have been emitted, again, according to the current electromagnetic theory. But that didn't happen either. So as Einstein looked at the problem, he made an assumption that had been made by Sir Isaac Newton. Again, we're not talking mechanics here. We're talking about light. Do you remember what he assumed about light? What was Sir Isaac Newton's thoughts about light? Albert Einstein theorized that light acted as a particle. The wave theory of light had been in place for a couple hundred years by this time. Newton originally said that light was a particle, and he explained many phenomena using that model. Afterwards, the wave theory of light took precedence. Now Einstein's going right back to Newton. And the observed energies of the light can be explained by Planck's law. E, the energy of the light, equals h, which is Planck's constant, times the frequency of the light. Now, earlier we found that the speed of light was equal to lambda f, so just substituting in for f, we come up with another equation for the energy of the light, energy of these photons. It would be h times the speed of light divided by the wavelength of the light. Actually, Max Planck did first apply his quantum theory to light trapped within a box. And he stated that if the light were in a box, it did act like a particle, but outside the box it acted like a wave. Einstein expanded on this and said light also acts like a particle when it's free, when it's outside of any confining box. He stated that light energy came in discrete packets of energy that were later named photons, again with the energy described by Planck. Thus, light is a group of photons which act like particles. This is a great example of how physicists continue to build on previous research. For example, Einstein used Planck's work, he used Newton's work, put them all together and came up with a new theory. The quantized nature of light explains both of these phenomena. The first one, the electrons, are emitted only when light's frequency is higher than a certain value, and the energy of these electrons that are emitted is not continuous, it has specific values. So what Einstein postulated is light's traveling as packets of specific size. They are packets of energy. These are the photons, which are particle-like. An electron from the metal that the light is incident upon is only emitted when a single photon strikes it. So a single photon hits the metal, a single electron leaves. All of the energy of the single photon is transmitted to the electron, which will free it from its orbit, and then it can leave the metal. Now, since the energies only come in specific measured quantities, that was measured, that was the electrons, so must the photons, which again provides more evidence that the photons are particles. Let's now look at a graph of the kinetic energy of the escaping electrons from the photoelectric effect. And here's the maximum kinetic energy here on the y-axis. And on the x-axis, we're going to plot the frequency of the light. This graph cannot be explained by wave theory. It indicates that light is made of particles, photons. Light is not a wave. This was shown earlier in the chapter. But what do you notice about the graph for low frequencies? And so low frequencies are down this side of the x-axis. At low frequencies, down here, below this cutoff frequency, we notice that no electrons are emitted. But now let's look at light with the frequency greater than this cutoff frequency down here. We'll see that it emits electrons with the maximum kinetic energy. And the higher the frequency, the higher the kinetic energy. But notice, where is the y-intercept of this line right here? Well, let's just extend it here. And we can see that it's intercepting the y-axis at a point less than 0. It's below the x-axis. What do you think that means? It means that not all of the photon's energy went into providing kinetic energy to the electron. Electrons are bound to their atoms in the metal. Remember, we've got the light incident upon a metal. So a minimum amount of energy is required to free them. We call this energy the work function. And the equation for the maximum kinetic energy of the emitted electron is Ke max equals HF minus W. Now let's look at what that looks like in terms of our old graphing skills. Y equals mx plus b. M is the slope of the line. Okay, so that's going to be h. B is the y-intercept, which is going to be w. So minus w is the y-intercept of the previous graph. All of the observed properties of the photoelectric effect were explained by Albert Einstein's work. And what's amazing is most people know Einstein for relativity and for writing a letter to President Roosevelt supporting the development of the atomic bomb for World War II. But the only time he received his Nobel Prize was for the photoelectric effect. Moreover, it reintroduced Newton's idea that light was composed of particles.
In atomic physics, energies are so low that it's awkward to use joules. A smaller unit of energy is the electron volt. Its value equals the potential energy of an electron in a region of space where the voltage is 1 volt. So you have potential energy is equal to QV, and we learned that when we did electricity and magnetism. And then we substitute in the charge on an electron, 1.6 times 10 to the minus 19th coulombs, in a region of space that is 1 volt. So the potential energy is 1.6 times 10 to the minus 19th joules. We will define that, that's what the 3 bars there mean, as 1 electron volt. So 1 electron volt equals 1.6 times 10 to the minus 19th joules. We've been using this version of Planck's constant, joule seconds, but now we're going to convert that to units of electron volt seconds when we deal with smaller energies. So here's Planck's constant that we've been using so far. Then we have a conversion factor here. 1 electron volt is 1.6 times 10 to the minus 19th joules. Do the division and the unit cancellations, right? You get the joules here canceling out. And you get this alternate version of Planck's constant. It's 4.14 times 10 to the minus 15th electron volt, or eV seconds. So, Planck's constant, same value, just 2 expressions. This is the one you use when you have energies in terms of electron volts, and if you have energies in joules, you use this one. To determine which value of Planck's constant to use in an equation, look at the energy units. Right? If you're using E equals HF and you have your energy in joules, use the Planck's constant with joule seconds. And if you have EV, you use the one with EV seconds. Use the conversion factor to go back and forth between joules and electron volts. So if you have an electron volt, multiply it by 1.6 times 10 to the minus 19th joules over 1 electron volt, and that'll give you your answer in joules. If you have joules to convert it to electron volts, you'll divide by 1.6 times 10 to the minus 19th. And again, just to remind you, 1 electron volt is 1.6 times 10 to the minus 19th joules. Stopping voltage. In classical mechanics, we could calculate the kinetic energy of an object by measuring its mass and velocity and using kinetic energy as 1/2 mv squared. Even though we know their masses, electrons are far too small to have their velocity measured directly. We need another approach to find the electron's kinetic energy. Begin with conservation of energy. If no work is done on the system, then a change in potential energy can cause a change in kinetic energy. So we're going to write delta KE is change in potential energy. Now, what's the change in potential energy? Well, that's equal to Q times delta V. Okay, so that's the change in electric potential times the charge equals the change in potential energy. So we now have change in kinetic energy is Q delta V. We just plug this in right over there. Now, although we discussed using a voltage difference to accelerate an electron, we can also use a voltage difference, and we're going to call that voltage difference V0. Okay, so delta V is now going to be called V0, and since we're dealing with an electron, we'll replace Q with E, which is the charge on the electron. This voltage difference can also be used to slow the electron, reducing its kinetic energy. So the change in kinetic energy is E times V0. If a voltage difference is applied to oppose the flow of electrons, and what's happening here? We've got the photons coming in here, it hits the metal plate and releases photoelectrons, which of course are negatively charged. But we're going to apply a voltage difference, so this is the negative side here, and this is positive. So what's that going to do? That's going to slow those photoelectrons down, right? Because it's going to put a force on them in that direction. So we will incrementally increase that voltage by using this rheostat. This will vary the voltage. So we'll incrementally increase until the voltage V0 needed to stop the electrons is found. This voltage is called the stopping voltage. The stopping voltage V0 is equivalent to the kinetic energy of the fastest moving electrons in a photocell. Working in electron volts simplifies the calculation of the kinetic energy. If a photocell has a stopping voltage of 3 volts, then the kinetic energy of the electrons is 3 electron volts. Right? Ke is EV0, so our kinetic energy is E times 3 volts, or 3 electron volts. Conversely, if an electron had a kinetic energy of 3 electron volts, the stopping voltage is 3 volts. So your Ke is EV0, V0 is Ke over E, 3 electron volts over E, we get 3 volts. We now have Einstein reintroducing Newton's idea that light was composed of particles, and his explanation exactly matched the observable data, which is great for the photoelectric effect and Einstein's career. But various phenomena have been explained by assuming light is a particle and some by assuming light is a wave. What is light really? We'll come back to that in the waves and particles topic in this unit. But for now, after some example problems, we'll move on to atomic models, which will lead to more surprises. A photoelectric surface has a work function of 3.84 times 10 to the minus 19th joules. What is the maximum kinetic energy that the electrons can have, given that their frequency is 6.22 times 10 to the 14th hertz? We write down the givens. Here's the work function, here's the frequency, and here's Planck's constant, and we'll use the one with joule seconds. Why? Because we have joules in the given. So our photoelectric effect equation is kinetic energy is HF minus the work function. So here's H, here's the frequency, and here's the work function we've substituted in our givens. Then just carry out the math, and you get the maximum kinetic energy will be 2.8 times 10 to the minus 20th joules. A photoelectric surface has a work function of 3.6 electron volts. What is the maximum kinetic energy that the electrons can have given that their frequency is 2.12 times 10 to the 15th hertz? We list our givens, and this time what's different? We're using Planck's constant in eV seconds, or electron volt seconds. Once again, we have the photoelectric effect equation. We have our kinetic energy is equal to the Planck's constant times the frequency. Here's our frequency, minus the work function. So we've substituted in our givens, carry out the math, and we get a kinetic energy, maximum kinetic energy of 5.18 electron volts. And here, just to notify you again, make sure we use units of EVs, electron volts, not joules. The nice thing about using electron volts is that often the energy does not need to be expressed in scientific notation. A photoelectric surface has a work function of 1.8 electron volts. What is the threshold frequency in order to eject electrons from this surface? We have our givens. Well, the work function's easy. Here's Planck's constant. We're going to use the electron volt seconds one because our work function is in electron volts. And here's the key thing right here. Since the problem states threshold frequency, that's the minimum frequency that will kick out an electron. That'll just barely kick it out. So we'll assume that maximum kinetic energy will be roughly 0 joules. So we have our photoelectric effect equation here. Kinetic energy is equal to 0. HF is equal to the work function. Divide both sides by Planck's constant. And here's our work function in electron volts. Here's Planck's constant in electron volt seconds. And we get a frequency of 4.35 times 10 to the 14th hertz. A photoelectric surface has a work function of 4.64 times 10 to the minus 19th joules. What is the maximum wavelength of light that will eject electrons from this surface? We've got our givens, the work function. This time it's in joules, so we'll use Planck's constant in joule seconds. We have our photoelectric effect equation. Now we want to work with wavelength. So what's frequency? That's c over lambda. So we now have kinetic energy is hc over lambda minus the work function. Now since we want the maximum wavelength, that's the same thing as the minimum frequency or threshold frequency. So in that case, the kinetic energy is 0. So we have hc over lambda is equal to the work function. We need to solve for lambda. So we multiply both sides by lambda, divide both sides by the work function, and we get this equation. So we're continued on the next slide. We bring our equation over from the previous slide, and then we just substitute in our givens. Planck's constant, the speed of light, 3 times 10 to the 8th meters per second, and here's the work function from our given, and we get lambda is 4.29 times 10 to the minus 7 meters, or in nanometers, 429 nanometers.